Today is March 16th, 2012, and this is AP Statistics at Berkeley High School. We're finishing up the last section of Chapter 12, the last section of AP material. So it's going to feel pretty good. At least I hope so. What we're going to be looking at today is transforming to achieve linearity. So we started this chapter by looking at regression and what it has to do with inference. We are going to take a very different turn in this second section. We're going to do no inferential statistics. We won't be looking at any H0 claims. We won't be looking at parameters versus statistics. It's all in 12.1. This section, transforming to achieve linearity, typically in our old textbook was taught like in chapter 2 or 3. The moment we talked about regression in general, we talked about these techniques. So let's get started. Here are the objectives for the day. Excuse me, I saw someone come in late, so I tried to change the attendance. Who just came in late? Oh, Mr. Davis.
He doesn't even say sorry.
Maybe he's not sorry. All right, so we're going to be looking at transformations to look using powers and roots to see if we achieve some sort of linearity. We will use the least squares progression line that comes out of those transformations to make predictions. And then we'll also be looking at logarithms in order to find whether there's whether there's a relationship between the x and y variables that may not necessarily be linear in nature. And we'll be looking at several transformations to determine which one does the best job for us. But let's go on. Let's get started. So, in the first half of this chapter, we said, hey, here's some variable x, some variable y, or explanatory variable x and response variable y, and then we would graph them. And if we wanted to use the procedures that we talked about in class, we said the relationship has to be linear. But relationships between variables are not always linear. Sorry, quantitative variables are not always linear. Are they, Paul? No, they're not always linear at all. A lot of times, the most interesting relationships are nonlinear. In fact, the most interesting relationship is probably an exponential relationship, where things grow exponentially, like population growth or money in a savings account, or at least back when they used to give interest on savings account balances. It's a pittance. It's a pittance. Very, very small. Okay. So, what are we to do? If our data isn't linear, and linearity is a prerequisite for using those tools, we have two choices. We give up, or we find somehow to make it look like a linear problem. And that's what the crux of this lecture is about. Okay? Applying some sort of procedure, and in this case, using logarithms or square roots or some other combination of things, to change the data into a new data set is called transformation. Now, we won't be doing it willy-nilly. We'll be doing it with thought and with purpose. But the idea is, can we take a data set and then say, does this data set lend itself to any particular model that's nonlinear? Can we take the nonlinear pattern, straighten it out by doing some sort of transformation, and in the process, if we find that a linear model is created from the transformed data, that transformation informs us about the relationship between the two variables. Let's do an example. Let's talk about pizza. So you order a pizza, and they're usually measured in terms of diameter, 10 inches, 12 inches, 14 inches. Well, let's take this example. I've got a 7-inch pizza. I've got a 14-inch pizza. Is the 14-inch pizza really twice as big as the 7-inch pizza? The diameter is twice as big, but is the pizza twice as big? Well, we usually think about the pizza not in terms of its diameter. I mean, we don't eat diameters of pizza. We eat areas of pizza. We eat wedges of pizza. A 7-inch pizza, 7 inches in diameter, is about 21 square inches of pizza. A 14-inch pizza, oh, I'm sorry, I did that wrong. Let me do that right. Let me get out of here. A 7-inch pizza, 7 inches in diameter, has a radius of 3.5. If I square that and multiply it by pi, I get about 84 square inches of pizza. If I take a 14-inch pizza, which has a radius of 7, and multiply it by pi, I get 153 square inches of pizza. Is a 7-inch pizza half the size as a 14-inch pizza? No, it's like a quarter of the size of a 14-inch pizza. The relationship here between the advertised size of the pizza and its actual amount of food there is not a linear relationship. Because as one doubles, the other one didn't double. What kind of relationship does it have? Well, instead of saying that that pizza has a linear relationship, we could instead say that it has a power relationship. Now, I don't believe you've ever run across the expression a power model, power relationship. But here's the idea. We don't believe that the size of the pizza can be predicted using a model A plus BX. That would be the linear model. Now, let me be more specific. Make A 0. When you have a 0 diameter pizza, you don't get a, there's no pizza there. It goes through 0. Okay? So we don't think that the model that predicts pizza size is linear. It's not a simple constant multiplied by our diameter. So what we could propose that maybe the relationship is a power relationship. Maybe it's some constant multiplied by x to some power. And if I knew what the constant A and the constant B was, then I'd be able to calculate, based on diameter, the area of the pizza. In this case, because area of a pizza has a square in it, I'm going to guess that that value of B is the number 2. And I'm going to guess, by the way, that A would be pi over 2. Take that diameter, divide it by 2, you now have a radius. Would that be right? Sorry, not pi over 2, pi over 4. Actually, they do the whole thing right there. All right. Now, in this particular case, we have perfect knowledge. We know exactly how areas of circles grow with respect to the diameter. I mean, if I had asked you what is the area of the circle before you came in here, you would have said pi r squared. You would have already known that the relationship of a radius of a pizza to its area is a squared model. But what happens when we're given data we don't know what the appropriate model is? Can we find out whether the power model is an appropriate one? Get rid of my writing there. Okay. Can we somehow look at data and then start fiddling around with it until we find out whether there is a particular model that works? Maybe it's a power model and we don't know yet what that value of P is. Let's try a procedure that may help us. Okay, we've got a fishing contest. And what I'd like to do, I'd like you to get your calculators out because you're going to enter in this data. Let me zoom in so you can see the data easily. There we go. The length is going to be an L1, and the weight you're going to put in L2. All right? So you get that data in your calculator. I'll get it in my calculator as well. Oops, I'm sorry. Here we go. Hold on. Thank you. Okay. Everyone got the data in? Everyone got the data in? So I've got my data in too. All right. So first things first. What's the data represent? L1 represents the length of fish. They're having a fishing contest. And in this fishing contest, you catch a fish, you measure it. But they don't want to do the contest by length. They want to actually do it by weight. But it's really hard to measure the weight of a fish accurately while on the boat. So, they like to do something easy, measure the length of the fish, but then they want to do something to that data, something appropriate to that data, to see if you can easily transform length of a fish into weight of a fish. In order to figure out what would be the appropriate manipulation to make, we have a bunch of lengths of fish and weights of fish. I think the lengths are in centimeters. Yeah, and the weights are in grams. Right? So first things first. Is a linear model appropriate for this data? Discuss. Why not, Paul?
Because the equation to find error.
I couldn't hear you.
I don't know. I just discuss it.
Well, the easy way to answer this question is no, it's not appropriate, because why else would I bring it into a lecture having to do with transforming data to make it linear?
The graph doesn't look linear.
What's that?
The graph doesn't look linear.
The graph doesn't look linear. Let me see if I can catch up to you, Katja. Second stat plot. Let me turn the plot on, and there's a scatter plot, L1 and L2. Zoom 9. Sometimes it doesn't work on the big calculator. Zoom 9. And you look at that data and you say, hey, does that data look linear? Is it? Did I not get one point in correctly? Do you have that? Do you have that weird point too? No.
Messed up.
I messed up.
Yeah.
Oh, not the first time.
It's okay.
It looked like the weight was too high. Can you find out? It's probably that one.
Yeah, it's only 69.
It's only 69? All right. All right. So if I do that and then I say graph, does that what your data looks like? Okay. So a couple warnings here. That doesn't look linear. Do you agree? That looks curved. I want to give you a warning that if you do a really simplistic attack on this problem, oops, up, over, enter. If I do a really simplistic attack on this data, where I do the linear regression L1 comma L2, if you look simply at the R value, you don't get the impression this is nonlinear. See how strong that R value is? Don't look at R value to determine whether something is or isn't linear. You use the R value to determine when you see something that's linear, how strong that linear relationship is. Do you hear the distinction what I'm saying? You can't use the R value as a yes or no for linearity. You can only look at it saying, once I've determined that the data looks linear, here's how I can determine the strength of the linear relationship. So, looking at the R value alone, we don't look at that. We look at that. We say, gosh, that kind of looks curved. What's the other thing? What's the other plot type that we can look at in order to determine whether the data are linear? The residuals. And to do that, I have to do a regression. Would you everyone do a regression on your calculator, please? So you need to use what? Stat calc 8. Do the regression so that you fill up the residual list. Linear regression A plus BX, yep. It's option number 8 on that calc menu. I've already done mine. And then after you do that, go ahead and go back to second stat plot. Oops. And what I would like to do is, I'd like to do the residual plot. I want to do not L1 versus L2, I want to do L1 versus second list resid. Mine is option 7, yours may be different. And then I need to do a zoom 9. And what do we see in the residual plot?
Not noise.
Not noise. Not disorder. We see a clear pattern in the residual plot. So this is, again, more proof to the claim that the data is not linear, are not linear. Okay, you're all convinced it's not linear. The relationship of fish length to fish weight, not linear. Well, what could it be? Well, I want to do an analogy having to do with two things that happened this week. You know what the two things that happened this week? One of them was Pi Day. March Madness. Syracuse almost lost. It would have been the first time that a number 1 lost to number 16. But no, that's not what I want to bring up. No, what I want to bring up is yesterday, the new iPad was introduced.
Yeah, what's the difference?
The biggest difference between the old iPad, the iPad 2, and the new pad called the new iPad, it's called the new
It's
iPad.
gonna be old in a few months.
Wait, is the new iPhone coming out in April?
There's no hints that, I mean, they just came out with the new iPhone in September, so they probably won't have another new iPhone until the fall. But one of the big new idea behind the iPad is that on this new iPad, the screen has a lot more pixels.
So it's like high tech.
In fact, it has the number of pixels on the iPad screen is now more pixels than on a high-def television,
That's amazing.
a 1080 high-def television.
I bet you Mac comes out with like a TV.
That's the other rumor. But let me get to the why, how this has to do with this particular thing. The way they made the screen with more pixels is that they doubled the number of pixels in the X direction, and they doubled the number of pixels in the Y direction. Question: how many more pixels does the new iPad have?
504 times more.
Quadruple is the right answer. When you double it in one direction and double it in another direction,
2 times 2.
yeah, it becomes 4 times longer. Okay, now what does that have to do with this fishy problem? Answer: is a fish a one-dimensional object, a two-dimensional object, or a three-dimensional object?
Fish.
Fish. Because they've got length, they got width, they got height, they're a three-dimensional object. So when we change the length of the fish, are we only changing the length and keeping all the other 2 dimensions the same? They're all changing. So here's an idea. How about we transform our data to bring that idea into our model. We don't think as we double the length, the fish's weight doubles. We think when we double the length, it changes 3 dimensions. So how can we do that? How can we transform this data to say, you know what, we know something about fish. Here's an idea. If we think, just like when the iPad doubled in both directions its number of pixels, why don't we take the length and say we're going to increase it, we're going to increase our explanatory variable, not just linearly once, let's do a cube. Let's take all the data in L1 and cube it to be respectful of the fact that fish are 3-dimensional objects. Now to do that, we can go up into the header of L3. You see how I moved up one and the L3 got as reverse type? If I go up in there, I could actually write a formula that will do something to every object in a list. And what I'm going to do is I'm going to take all the data that's in L1, so I went second L1, and I'm going to take it to the 3rd power, caret 3.
Fish aren't cubes.
No, but they are 3-dimensional objects. And all I'm going to ask is, after we do that, after we take all of that data and say, here's the cube, is there a linear relationship between the cubes of the lengths of the fish and the weights? Maybe? I don't know. Let's find out. So I got to go to second stat plot, and I'm now proposing that we are going to do a scatter plot, which is number one, the first of the plot types. But I don't want to do L1 versus resid now. I want to do the cubes of the lengths of the fish, which is L3, and I want to I want to look at the graph against their weights, which is in L2. So does everyone caught up with me? The cubes of the weights is my x value, and then the cubes of the lengths of the x values, which are those in L3, and then their weights are in L2. I suppose I need to plot this now. Zoom, oh, sorry, I really screwed up again. Zoom 9. What do you think? Does the pattern look linear now? It certainly looks a lot more linear than before. This act of choosing a transformation, and when we get the linear pattern, we believe that we've actually achieved some insight about the relationship of those variables. The cubes of the lengths versus the weights does create some sort of predictable pattern. Hey, I wonder what this equation, what the line of best fit is for this data. Because maybe then we can use it to make predictions. How much should a 20 centimeter fish weigh? Well, let's try this out. Let's take the data and let's find the linear regression for this transformed data. Stat, calc, 8. And I want to find the regression model. I want to find the line of best fit for the cubes of the the cubes of the lengths versus the weight. So here's where it becomes tricky. I can't just hit enter here. I've got to do more. By the way, I think I heard false. No. L3, L2. Remember, the cubes of the weights are the predictors, and L2 is the response. So I want to say my X data is in L3, and my Y data is in L2. Now, I run the regression. A couple things that you may notice. Look at the R value. Do you remember what our old R value was? It was like 92 or something. Look what happened. It got stronger. That's a good sign. It means that our data does seem a little bit more linear. Now, let's take this information and say what we have. The linear regression model that comes out of here is y hat, a predicted y value, is equal to A plus B, and now I'm going to pause. You want to write X here. But what was the data list we used for X's? It was L3. L3 were all those lengths cubed. Really what we have found is a model that looks like y hat. If I want to predict the weight, I take A and add on to it B times X cubed. The question is that a reasonable model for that data?
Yes.
Okay, 406 and point 0.146. Let me write that down because I'm going to try something out here. 406, 407, let's say, plus 0.0146 times x cubed. Let's see if I can take that particular equation, 407 plus 0.046 x cubed. I want to graph that, and at the same time, what I want to do is I want to put the original plot up, which was L1 versus L3, or L1 versus L2. Zoom. Crashes on me. Zoom 9. There's the data. And there's an equation that we think models the data. How did we do? Pretty good. Now I want to ask the question, how much should a 20 centimeter fish weigh? Plug it in. Okay. I could do this. Trace, and I could type in 20 for X. Is that not how it works? Second calc. Value. There we go. And I can type in 20, and I can go along that equation, and it says, oh, a 20 centimeter fish should weigh about 121 grams. How much should a 40 centimeter fish weigh? Oh, about 938 grams. In other words, I can move along that. That prediction line to make reasonable guesses about how much these fish should weigh given a particular length. And this model fits our data much better than the linear model. Are you understanding what I'm saying? Now, this works because we happen to have a little insight about the dimensionality of fish. We know that they're three-dimensional objects. Let me take another crack at this with another kind of data set. We have already done most of the example that's in this. We did it by hand. They actually did it another way. They actually took the cube root of the weights. I think what we did was fine. So we're gonna scream through this, and we're going to talk about. They go through two different ways of trying to do that transformation. We use the one where we raise the power of every x value to some. We took the power of every x data and transformed it. And again, they're saying the other way to do it is to take the root of every y value, and you get about the same. I'm not going to make a big distinction between those two methods. All right? But what if you have no idea what power to choose? You suspect that there's a power relationship between the x data and the y data, but you don't know what the power is. What can we do? Well, we got a method for that. Some pieces of statistical software have a little slider where you keep on changing the power until you get to the point where the data actually matches the prediction line. But there's a more efficient way of doing this, but it involves logarithms. Now, luckily, every single one of you have taken Algebra 2. Yes? And every single one of you have learned about logarithms in Algebra 2? You don't remember them? Okay. What ends up happening? I'm not going to end up pushing you too hard on your memory of logarithms. You have to know that a logarithm exists. And if you do that, and you remember one other thing, which is that we undo a logarithm with a function called e to the x. If you're solving an algebraic equation and you go x plus 5, you undo the plus 5 by subtracting 5. We say that addition and subtraction are inverse operations. If you have 5x is equal to 10, to undo the 5 in front of the x, you divide by 5. We say that multiplication and division are inverse operations. Well, what we're going to do is we're going to transform the data using natural log. And we're going to undo those transformations by using a function called e to the x. So, not every curve relationships are power models, for example. Some of the relationships can be described using a logarithmic model, a plus b log x. Sometimes the data x grows in a way in which you start with a value, and let's say it doubles every 4 hours, like bacteria growth. Yay, bacteria growth. Boo, bacteria growth. I'm not sure where you fall on the bacteria growth. Say that again, Sam?
She said it depends on what type of bacteria.
Because isn't some bacteria good and some bad or
That
something?
is true, some bacteria.
Yeah.
Like
Ebola.
Ebola, not good.
Bacteria.
Oh yeah. But some bacteria are necessary in the production of food. I think yogurt has live bacteria in it, and cheeses, I believe. I love cheese. How come they don't have cheese yogurt?
That would be
Well, certainly certain foods should never be put together.
Cheesecake is sort of like, well, it's not yogurt, but it tastes like.
Well, cheesecake isn't cheese; it's cream cheese. So the cheese in cheesecake is spread with cheese. Anyway, so
Cheesecake is cream cheese.
yeah, it's made of cream cheese with lots of sugar in it. Yeah, certainly not cheddar. All right, so certain data have this relationship where you have a doubling over time, like bacteria growth, or you have much slower population growth, so it's still done as a percentage. Woo! It's still done as a percentage. Or you could say budgets grow this way. Every year, budgets for schools need to grow by at least about 2%, simply to keep up with the increased costs associated with running schools. Increased salaries for teachers who get old like me. Stuff like that. So, if it's multiplicative growth, it grows by a particular percentage. That's an exponential model. And it's modeled by the equation y is equal to ab to the x. Okay? So y equal ab to the x is actually a model that shows up a lot. And what we need is a plan to be able to say, hey, I've got some data. Is this data growing using this particular model? All right? Okay? So, the kinds of models that we may have to choose from. The exponential model, y is equal to ab to the x. I'm sorry, I can't say that without thinking about, when I was growing up, there was a radio station in Detroit which was WABX, but it's no longer there. It's now, it used to be a great rock and roll station, and now it's a young country, I think. 99 and a half. But you guys don't listen to radio, do you?
Yeah, sometimes. I don't bring my iPod cord in.
106.7 the D.
Well, you have to.
97.1.
Classic rock.
97.1 is the ticket. That's the sports. It's not,
Yeah, but it's a great station.
it's not even music.
They play some music.
Yeah, like it's coming back in commercial.
Okay.
Like when they switch.
Well, if we start with
Like 3 seconds. Elevator music.
If we start with an exponential model, and we take the log of both sides, there's some things that we can do to manipulate this algebraically. Now, the log of abx, or ab to the x, by the law of logarithms, can be rewritten as the log of a plus the log of bx. This is a property of logarithms that you should have learned either in, again, in Algebra 2 or in pre-calculus. There's another property of logarithms that says that if I have something like bx, I can take that x and bring it down into the front. Which means that I can take the natural log of both sides and I get an equation that looks like log of y is equal to log of a plus x times the log of b. Now, because a and b are constants, the log of a is a constant, and the log of b is a constant. And so what we end up getting in this process is we get log y is equal to a constant plus a constant times x. Log y is equal to a constant plus a constant times x. Well, that's a linear model in itself. Linear models that we've been playing around with are things in the form y is equal to a plus bx. Well, let's say that a is the natural log of a. Let's say that this b is the natural log of b. It's a general model. So what we leave here with is, if I take the logarithm, I don't know why my voice is cracking, if I take the logarithm of all my y data, and I get a linear relationship, that is proof that the original relationship was exponential. Say that one more time. That's what the screen says. It says, if you have a data set X and Y, and you believe the relationship between X and Y the relationship is exponential, meaning that the Y values are growing using some sort of multiplicative rule. They're doubling every 4 hours. It's getting bigger by 2% every year. If that's what your Y data looks like, if you take the natural logs of all the Y data and then map them against your original X data, if you get a line, that's proof, it's evidence to the claim that the relationship is exponential. So, should we try this out? We're going to try it with fake data first, and then we'll do real data after. You ready? Fake data first. So back to the calculator. We're going to go into our data, and I'm going to clear out all the data that we've already put in there. We're all done with it. Okay? Since I've already said that bacteria growth is something that looks like an exponential model, let's do that and let's see how this looks. So, I start with one bacterium at time 0. Whoops. Oh, that failed. Stats. Edit. 1. Enter. Okay, great. So at time equals 0, I got 1 bacteria. How quickly is this bacteria going to double? Give me a number. Every 3 hours it's going to double? 3.5. Oh, you're going to make it hard on me.
3.3.
How about 3? Let's just make it easy on all of us.
Oh,
So 3 hours later, 3 hours later, how many bacteria are there? 2. Okay? 6 hours later, there's 4. Right? Oops. 4, enter, and I'm going to go over here, and I'm going to put 6 hours. Okay? And then 9 hours later, how many are there? 8. And 12 hours later, 16. So after 12 hours, there's 16. I think we only need 2 more. 15 and 32. And 64 is the number after 18 hours. Okay, let's take a look at this. Let's take a look at this data. Second stat plot, and I want 1 versus 2. That's exactly what I want. All right, and then I'm going to go zoom 9. Oops, I still got that y equals stuff going on. Let me get rid of that. Okay, so there's my graph. Does it look linear? No, it looks curved. Many people refer to this kind of curve as a hockey stick curve. It starts very, very slowly, and then it jumps up. Right? What if I made, again, purposely making a mistake? What if I did stats, calc, 8, L1, comma, L2? What if I asked, what is the linear relationship between this data? Look at that, I got an 0.87 R value. That's a strong linear relationship. What was the error that I just made again? It didn't look linear, so I shouldn't be asking what's the strength of the linear relationship. Let me do that other thing that we did before. Let's look at the residual plot. Second list resid. Do you see a pattern in the residuals? Is there a curved pattern in the residuals? Probably easier to see if I didn't zoom 9. Let me try that, zoom 9. There you go. It's a clear curve pattern in the residuals. So we've got evidence it didn't look linear in the original, and we see not noise, we see a pattern in the residuals. It's not linear. So how do we show what it may be if it's not linear? We suspect that the relationship is really exponential. So I'm going to transform the data. I'm going to transform the data by taking all of my y values, and I'm going to take the log of the y values. Now I'm going to use the natural log, the log base e, and for every piece of y data, I'm going to do that transformation. So that takes all my data in L2, it takes the logarithm of them, and puts it in L3.
What you just do?
I went up into the header, so up into the top of L3. Let me clear this so you can see it happen again. Up into the header of L3, so I've got reverse type there, natural log, and then I'm going to say, what list do I want to transform? I want to transform all the members of L2 and create a new list and put it in L3. And what do we have when we do that? If it really is an exponential relationship, our scatter plot now should look linear. Let's try. Second stat plot.
How should I do the natural log it? Just commit it to yourself.
If I suspect something is exponential, the inverse of that relationship is natural log.
But like last time you cubed it.
Last time I cubed the x's. Because I thought if you multiply the length, it'll give us some sort of relationship that represents the length, the width, and the height. So I suspected, and so I tried that out. I suspect that this is exponential, so I used logarithm to undo that kind of doubling behavior.
What if we natural log less?
We're going to in a second. All right? So let's take a look at the relationship between L1 and L3 now. This is L1 is the X data, the hours, and L3 is the log of the number of bacteria. Hit enter, zoom 9. So what do we see? That looks linear. So, if after taking the natural log of all the y data, we get a linear pattern, x versus natural log y, our conclusion is the relationship of these two variables is exponential. The other part of what we need to do then is to say, if there is a relationship and it's an exponential relationship, what is the equation that allows me to know how to find a y value given an x value? Remember how we did that with the fish? How much should a 20 centimeter fish weigh? We could put it into the model. How much bacteria should I have after 5 hours? Or after 24 hours, given this particular model? Well, let's do a linear regression on this data. On the linearized data, the transformed data. Stat. Calc 8. L1 comma, and I want to make sure I did this right. L1 comma L3, the transformed data. Perfect line. Also, remember, we made up that data. That wasn't real data. We said explicitly, it doubles every 3 hours. And when you do things like that, yeah, you get perfect linearity out of the transformed data. So here's what I see. If the relationship of what we had was the natural log of y is equal to A, which is 0, plus B, which is 2.31049.062 to the x. If I want to find, oh, sorry, that's y hat. If I want to undo this so I can get a y hat all by itself, I do e to the x on both sides of this equation. I take this natural log of y hat and I make it the power on e. I take this stuff, I make it the power on e. I do the same thing to both sides of the equation. I'm undoing the natural log. E to the natural log of y is just y. E to the 0th plus this is equal to e to the 0th, 0th, yes, times e to the 2.31049.602x. All right? Last part. E to that power is just a number. I'd like to know what that number is. E to the power of 2.31049.060 or 062. What is that number? 1.26? 1.26. Give me more.
Oh, I mean, that's
1.2599. Give me more. What?
2105.
2105. Now, I'm asking you to give me all those decimal places because rounding has really weird effects here. So I don't want you to drop any decimal places into the very, very end. All right? So that's what we think. 1.25992105 to the x power. Now, if this really is the model, what should be able to happen? I should be able to take this equation, map it against our untransformed data, and I should see a good fit. Let's try this out. Close the ink layer. Let me put that equation in. 1.2599. Lost it already. 2105 to the power of x. All right, there's my graph. Let me go back and let me put the scatter plot in there of the untransformed data. L1 minus L1 versus L2. Let me graph them side by side. Oops. Let me do a zoom. It's not linear. But what do we think about the graph that we just found? What do we think about the equation that we just found? Does it go through the data? If I said second calc value, I wonder how many bacteria we have at 4 hours. Oh, not 4 hours, 6 hours. Oh, our graph matches exactly the data that we had tried to model. So, taking the natural log of all the y data and getting a linear line shows us that the relationship is exponential. Okay, how many people in here are interested in business and finance as a possible career? None of you? Corporate America making lots of money? Yeah? This is really important to this. Okay, so much so that when you look at stock prices over time, and stock prices for good companies grow exponentially, when you look at stock prices over time, they do this transformation on their graphs. You don't see equal spaces for equal amounts of different values of money. Instead, they put it on a logarithmic scale so you can undo the exponentiation of it, and you can see a linear pattern. This is highly embedded into finance, stock prices, banking. This is really important stuff. All right, we are running out of time. Okay, I have a favor to ask. There's an example in the book, and when we start class on Monday, there's a lot of data that I want you to pre-enter your calculator. It has to do with Moore's law. Moore's law is a conjecture that was done by an early founder of Intel. Does anyone know what Intel is? They make computer processors. Moore conjectured that the number of transistors on a CPU will double every 18 months. He conjectured this in 1965. Moore's law ends up not actually being true for processors, but it also ends up being true for just about every single aspect of computers that you buy. My first computer, my first real computer that I bought. Take a guess at the hard drive size. 2 megabytes? No, it's a little bit bigger than that. 20 megabytes. The whole hard drive, 20 megabytes. How much data does a typical MP3 have? Okay, the whole entire space of my hard drive was about a song and a half. Hard drive sizes have doubled and doubled and doubled and doubled again over the course of my lifetime. Now that computer was purchased in 1989. Well, think of processor speeds. What's the typical processor speed now? No, those are measured in megahertz. Onboard memory. Everything about a computer is essentially doubled about every 18 months. Hard drive size, onboard memory, processing power. If you're trying to project how powerful a computer will be 18 months or 2 years from now, you can use Moore's law. Hi, have a great weekend.